Lecture 10, we are going to discuss yet again titration curves. This time around, I'm going to show you an example involving a weak base being titrated by a strong acid. And such type of curves have a similar look to the ones we saw in the previous lecture, except that because you start with a weak base, the pH starts high to begin with, and as you keep adding strong acid, the pH keeps dropping until ultimately you end up somewhere low in pH. So this is almost like the mirror image of the pH titration curve that we saw for weak acids, with the titration of strong bases, right? So we're going to look at each one of these points. We're going to start with the initial point to determine the pH of a basic solution prior to adding the strong acid. Then we're going to move into the buffer region to calculate different pHs within the realm of the buffer as we're adding HCl and we're creating conjugate acid. We will also calculate the equivalence point pH, which for a weak base titrated by strong acid has to be less than 7. And then we will also look at a data point in the excess region where we have added more HCl than we needed to reach the equivalence point. So let's get the process started. Let's look at the initial point. Here we have pyridine, which is a base, and the way we tell that this is a base is by looking at the kind of K value that we are provided. This is the Kb value, meaning that the substance is a base, and it does behave as a basic substance, and in relation to water, not only will it behave as a base, but by default it will have water acting as an acid. So the base will accept an H+, going from aniline to anilinium, or yeah, actually this is not aniline, this is something else. This is I think this is piperidine. Yes, so this is piperidine and that's piperidinium. That being said, the name doesn't really affect things at all. The point is that you are taking up an H+ for the base and you're removing an H+ from the acid, so you end up generating hydroxide in this base equation. So what we do is, at the initial point, set up your typical ice table. The initial concentration is 0.1 molar for the base. Nothing is being said about the conjugate acid or the hydroxide, so we assume them to be 0 to begin with. And then the change is going to be minus x, and plus x, meaning that the equilibrium concentrations will be 0.1 minus x, and x. Alright, based on that information, the equilibrium expression for the initial point will equal, oh yeah, and by the way, before I get into that, let's take a look at the ratio of the initial concentration and the Kb value. Here we get a value that is less than 400, so unfortunately that means that we are going to have to use the quadratic formula. Alright, so here we go. We have products multiplying each other divided by the reactant, so we have x squared divided by 0.1 minus x, and that equals the Kb value of 1.33 times 10 to the negative 3. Since we cannot neglect the x, we're going to have to cross multiply by 0.1 minus x to yield the following equation. We're going to move everything to the right side of the equation so that we have 0 equals x squared plus a term times x plus some other term that doesn't have x's. And so this sets up the setup. Oh, what am I saying here? This gives you the material necessary to perform the quadratic formula equation to find the value of x. So we're going to input the value of b, which is positive 1.33 times 10 to the negative 3. We're going to input the value of c, which is negative 1.33 times 10 to the negative 4, and the value of a, which is 1. So we input all that in the equation. The fact that negative b is negative implies that the plus or minus is really only going to be plus, because the value of x at the end has to be positive. Alright, so we multiply negative 4 by negative 1.33 times 10 to the negative 5. That generates the positive number you see here. We also square the 1.33 times 10 to the negative 3 to get the 1.77 times 10 to the negative 6. Adding those numbers together and taking the square root of it ultimately generates the value that you see here. So adding that to negative 1.33 times 10 to the negative 3 and dividing by 2 tells us that the value of x is 0.0109. Alright, so with this value, we go back to the table. X represents literally the hydroxide concentration. So if we take the negative log of that, we're going to get the pOH automatically. And since what we're really after is the pH, we just need to remember that this needs to be subtracted from 14. Meaning that the initial pH is actually pretty high. It's up to 12, a value of 12.04 pH units. So this indeed is a very basic solution. Okay, so we got the original pH of the weak base. Here is where we're going to start introducing the strong acid and basically entering the buffer region of the titration curve. So here we go. When we add HCl, automatically the strongest acid present in solution will not be water, it will be the HCl itself. And since HCl is a strong acid, technically this will dissociate into H+. Okay, so you can rewrite the equation so that you have H plus or H3O plus as the reactant. This is basically the HCl being added to the reaction. The base is going to acquire the proton. The H plus is going to be taken up, so this becomes water again. So let's take a look at the concentrations. Assuming that we have 20 mLs of the base, this is something that you will have to be told in the problem at the very beginning, right? So this is not something you're going to be expected to just like guess a volume for the base. No, you'll have to be told that. But we're going to have 20 mLs of base with a concentration of 0.1 molar. And over here we have a concentration of 0.5 molar for HCl, and we're adding 1 ml worth of it. So if you multiply the mLs by the molarity, you will get the millimoles, right? In the case of the base, we're dealing with 2.00 millimoles. In the case of the acid, we have added 0.5 millimoles. So the MICE table will tell you that the limiting reactant is the 0.5 millimoles of H+. So subtract that from both reactants, add that value to the product. You'll find out that you have 1.50 millimoles of base and you have generated 0.5 millimoles of acid. Okay, so now we get to use the Henderson-Hasselbalch equation because we're dealing with a buffer at this point. And we know that to be true because we have non-zero values for both conjugate acid and conjugate base alike. Now, in order to use the Henderson-Hasselbalch equation, though, you do need the value of the pKa. So we're going to take the Kb value, take the negative log of that, that will give us the pKb. Okay, in this case, 2.88. And if we subtract this value from 14, that will give us the pKa value. Okay, so this is a must. You have to have the pKa value if you're going to use the Henderson-Hasselbalch equation. It doesn't matter if the original species is acidic or basic. The equation calls for the pKa, so you have to get the pKa if you don't have it. All right, now that we know that the pKa is 11.12, and by the way, the fact that this pKa is greater than 7, this is telling you that this is probably a basic substance. Now we're going to input the millimoles. The base is the species right here, C5H10NH. In other words, the species with a lesser amount of hydrogens. So we're going to input 1.50 millimoles on top. And for the acid, which is the species with a higher amount of H's, we input the 0.5 millimoles on the bottom. And when you take the log of that ratio, you're going to find out that equals 0.48. Being added to 11.12 gives you a value of 11.6 for the pH. Alright, so if this was done correctly, because we have added an amount of HCl, the pH should have dropped down from the original value. So let's see if that's the case. This is 11.6. The original pH was 12.04, so this indeed went down. So this is looking good. Okay, let's take a look at the addition of another ml of HCl. So now we have a total of 2 mLs of HCl added. Multiply molarity by mLs, you get 2 millimoles for the base. You end up with 1 millimole for the acid. Based on the table, the least amount is the 1 millimole, so you subtract 1 millimole from both and you add 1 millimole for the product. And this will tell you that you have 1 millimole of base remaining and you have generated 1 millimole of acid. And because the two amounts are equal, what this means is that when you use your Henderson-Hasselbalch equation, the log of base over acid basically will go down to 0. It'll cancel out entirely. So you are dealing with the midpoint. The pH equals the pKa. This is the midpoint of the actual titration curve. And once again, the pH in fact has gone down upon adding more HCl. Okay, let's do another one. We're going to add an extra ml of HCl, in which case the millimoles are now 2 and 1.5 millimoles. Based on the ice table, subtract 1.5 from both reactants, add 1.5 to the product. You now have 0.5 millimoles of reactant left over. You have 1.5 millimoles of conjugate acid product produced. Base goes on top, so the 0.5 needs to go on top. The 1.5 is the acid that needs to go on the bottom. The pK is still 11.12. So if you perform the division and take the log of it, you'll find out the number is negative 0.48. So add that negative number to 11.12, and you find out that the pH is now 10.64, which in fact is lower than the previous amount that we calculated. So this is actually looking pretty good for the titration of the weak base with a strong acid. All right, now in the next video, I'm going to show you the calculation for the equivalence point and the calculation of the pH past the equivalence point. So I'll see you in the next video.